You ready to get started? Okay. Well, thank you everyone for coming to the System Engineering and Operations Research Seminar. We're delighted to have Suvrajeet Sen give a talk with us today. So he is a professor at the University of Southern California in their Industrial Systems Department. He's also been a faculty at the University of Arizona, and he has been a program director at NSF in the Service Enterprise Systems. He is has been associate editor of a number of journals, Operations Research, and Forums, Journal on Computing, and he is very prolific in publishing, doing research in optimization, stochastic programming, and I think he'll be talking today about kind of integration between optimization and machine learning, and I think he has some examples that you give in some of your classes that you teach in data analytics, so look forward to what you have to say.
Thank you very much for having me here. We were talking about, Carla and I were talking about systems engineering, and the reason I loved being in the University of Arizona was their department used to be systems engineering originally and then systems and IT. It brings a different flavor, and actually this kind of a talk puts those different flavors of OR and industrial engineering and statistics together. And so learning about studying systems engineering gives you actually the tools to go across a variety of problem classes. And so happy to be here in this department. Okay, so let me quickly mention the source of a lot of this work are my current PhD students. There are two others that are not mentioned here because they haven't yet written the papers that come with it. They have done some of the work, but these two up here have actually written some of this work. And then there is some work done by former students as well. So very fortunate to have the inspiration from these guys. Other than those guys, there'd be no such talk. I'm going to mention some of these problems as we go, but I thought I should just give you a sense that when you combine optimization and statistics together, it gets more real as a real-world problem. But on the other hand, there are also many more mathematical challenges that open up. And those challenges we may not really have the tools to address as we know mathematics, statistics, optimization today. Let's go on with what my overall plan is. What I'm going to try to do is to first look at what stochastic programming problems look like. And you would be surprised to know that I'm particularly disappointed with the way stochastic programming has evolved in the last maybe 20 years. Prior to that, we did not have the computing power to do anything really serious with stochastic programming. But for the last 20 years, we've had very good machinery around, and yet we have stuck ourselves in the 1950s paradigm of stochastic programming. And I'm hoping that I can rub enough people the wrong way to start thinking about new ways to address these problems. I'm going to talk about this new class of problems that I'm calling LEO models, which are a combination of these two. And again, this is not the answer to everything, but it's a class of problems. I'll talk about why we need to look at the curse of dimensionality beyond just the lip service of the curse. So we need to see how we can combat this, and it depends on the class of problems you're studying. I'll talk about a certain thing that I'm calling model assessment and selection, partly because a lot of times what happens in stochastic programming and what happens in deterministic optimization seem to be pretty similar, and it should not be the case. Because in deterministic optimization, you are setting yourself in the world where everything is known, there's not much variability, and when you say, here is what I will do, you can do that and expect that the system will respond in the manner that you expect it to respond. In the stochastic programming world, you first said that there is uncertainty. Okay? And then in the 50s, when Danzig posed the problem, it was fair enough to say that I know the probabilities. But then we didn't even have LP solvers. I mean, 1955, there was not a single large-scale solver. Okay, at that point, you can state the problem and say, okay, we are doing some hypothesis here, that we know some things. Today, in this highly data-rich world, okay, we ought to have moved further from that paradigm of saying, here are my distributions, here I'm going to solve this problem with these distributions. And more importantly, at the end of the solve, I want to see how well the model might do in the future. Okay? And so somehow, simulation should become our close ally, or at least some sort of validation process should become our close ally in stochastic programming. We do none of that. Here's what we do. Uncertainty will create a set of scenarios, and now with those scenarios, if we can set up a deterministic equivalent problem, we will solve that, and then we will say we've solved the stochastic programming problem. Unfortunately, the decision maker has to take that decision and now face the uncertainty. The uncertainty hasn't gone away. Just because I've solved this one instance, the uncertainty hasn't gone away, because we're still going to not know what is going to happen in the future. What are the range of things that can happen in the future? They have no idea. And what we've done is we've taken this uncertainty and hypothesized one distribution. We've hypothesized a scenario, and those scenarios, if things happen outside the scenarios, well, what? What should we do? And that's what this model assessment and selection is about, that I'm suggesting not to just try one set of scenarios. Go ahead and examine other possible outcomes, other possible settings, and then decide which of these models is best. Now, how do you decide which of these is best? We do that in optimization. We do that in statistics a lot, this model selection paradigm. And why not optimizers try to use that same kind of paradigm to say, let's see how a certain decision might perform once you've implemented it. How might it perform on scenarios that you didn't ever create, right? So that's the mindset that I want to get across. Okay, and then I'll show you some examples and those kinds of things. So, okay, so hopefully I'll just set the differences and similarities between optimization and learning. Okay, some of these are very similar terms, but their roots are different. So stochastic programming comes out of the optimization world. Statistical learning comes out of statistics, of course. And some of the distinctions may not always be completely clear-cut. They draw upon sometimes very similar mathematics. So I'll point that out as well. So let's talk about what are we doing with stochastic programming. We're optimizing decisions. In statistical learning, we're also doing some optimization, which is usually this best parameter fitting optimization. Okay? And as a result of the differences between decisions. In decisions, we often come across inequality constraints. This sort of one-sidedness, I should be on one side of the budget, I cannot exceed it, or I should be, my variables should be in certain ranges. Those are all inequalities. Whereas in the parameter fitting world, it's more either unconstrained parameter fits, or if it is constrained, there are equality constraints that you have to satisfy certain relationships between the performance of a system. And those relationships are usually in terms of a dynamics of the system or something like that, an equation. So in that sense, these optimization problems have slightly different structures. But ultimately, when we do something like sample averaging, these guys call it empirical risk minimization, but they're the same things. You're taking observations and you're somehow calculating a sample average. In one case is the name, empirical risk is the other name. There is no real risk that is being modeled by this kind of optimization. And by real risk, I mean that in operations research, we usually think of risk as being some sort of measure of outliers, whereas this is not the outliers business. This is simply the average. Okay, going on further, mathematically speaking, they actually both derive this sample average approximation and empirical risk minimization. Both can be justified using this convergence ideas of sampling plus uniform convergence. Both of those rely on that theory. And I'll talk about what that theory does eventually. But the algorithms certainly look similar in some cases. So this SA is stochastic approximation from the 1950s, 51, and both have drawn upon stochastic approximation. But the mainstay of stochastic programming has been this L-shaped / Bender's decomposition. Part of the reason for that is that we're dealing with inequality constraint problems, as well as representing the uncertainty in a manner that you can decompose the large-scale nature of the problem. And I'll talk about how a lot of the folks on this side don't really recognize the existence of this side. Needless to say, a lot of people on this side don't recognize this side either. So, all right, so I'll talk about certain things like confidence intervals, but more importantly, this notion of prediction intervals. Prediction intervals are intervals that decision makers ought to know about what range of things can happen with the next outcome that they observe. In our optimization world for stochastic programming, we typically do not give that kind of information. And that's very critical for decision makers, for decision makers. So a few more things, we don't do as much validation analysis as we should. I'm going to talk a little bit about that. So the agenda is quite large here, and we may not be able to make it the whole way. And if some of you are there at the Informs conference, I hope you come to my tutorial and we'll finish the whole thing. But there I have an hour and a half, so I can finish the whole thing. All right, so finally, this side, I would say, is more or less optimization-enabled learning, because learning is being used to describe how you characterize the data, and how you characterize the data is being done by fitting some parameters, and that parameter fitting is the optimization side of learning. And for our purposes, I'm just going to leave this as a question mark here, because although I would love for people to use learning-enabled optimization, because that's what I'm trying to do, I'll show you what I mean, but you're all free to choose your own little favorite acronyms. My acronym is pretty cute, I think. All right. Let me go to stochastic programming first, okay? And here, there is a problem where you have a function c of x. This is the cost that you're able to predict accurately. And then there is another part of the cost that you're really unsure about because of the randomness and the uncertainty involved. Okay, and it can be much more complicated than one function, because this function h could really be a composition of many functions. So, for instance, if you have cost of the next period and the period after that and the period after that, all of those can be composed into one function again. So you could have a telescoping sum there, but I'm not going to go into that complication because just one function is bad enough, as we will see. And so here is one function, and one type of function looks like this. That's a solution to a linear program. But this could be other things. There could be a QP. There could be any other kind of function which shows up here. But the main point is that you choose one, you make one choice, and then there are future decisions that depend on these omegas. And in the simplest case, in this simple case, you have only one omega. Otherwise, you might have a sequence of outcomes, and that those sequence of outcomes may happen probabilistically, and then you have the function h become a lot more complicated. In any event, all of these seem like value functions of constrained optimization problems. And so let's go on to now what we do with that problem. We, of course, don't have a distribution. That notion of having a distribution is either a subjective thing, or you have some data to support it, or you do something of the following kind, which is this empirical observations. You take your observations and you do 1 over n, and now you got this sample average approximation to the real problem, so to speak. And what the statistical learning community calls this is empirical risk. Though I like the word empirical because you're using observations of the data to create this approximation. The word risk is probably misplaced, but let's leave that there. This often goes by the term data-driven optimization. Not so sure exactly whether it's fully data-driven, but the point is that you don't necessarily have to have the distribution set up. You can just take the data, stick your 1 over n, and that gives you your empirical distribution, so to speak. Okay, so an example, I'm going to borrow this example from learning just because I want to make the point that a learning problem can be set up as a stochastic programming problem as well. So this is a support vector machine. And in this SVM, you have two kinds of pluses. There is the red plus, and this, I believe, is a green plus. I don't know. I mean, I'm not so good with colors. This could be orange. That could be yellow. I don't know.
Green and red.
Green and red, okay?
Yeah.
Okay, thank you. So, this axis is, so these x1 and x2 axes, these are usually called predictors or features. And so this x1 axis here could be, so if these points were about cancerous, so cancerous cells here, non-cancerous cells here, so the reds are non-cancerous, the greens are cancerous, and then this could be the size of the tumor, this could be your family history, and now you've got two predictors that are being used to predict whether your particular cell is cancerous or not, without doing any further testing. Right? So if that is the case, then you would try to find this kind of a hyperplane which separates the two sets. And so if you didn't want to do further actual tests, you take a look at the image of your cancer cell, take a look at your family history, make a prediction whether you have cancer or not. Otherwise, you might have to make an invasive test. Who knows? All right, so if you want to do that, then you want to find the plane that separates the points, and that's a quadratic program of this nature. Let me describe what this notation means. Oops, excuse me. What happened there? Okay, so the predictors are those two axes, the size of the cell and the family history. And the W is whether you are cancerous or not. And then, so the problem looks something like this, which is find a plane. A plane, of course, has a constant term and the normal to the plane, beta 0 and beta. And so find the plane which is such that this future is this future being, this is the data side. So this quantity plus so this is the error. This is the error. So this is the sample average error. So these betas are like the first stage decisions X. Okay. And these deltas are coming from what may happen from the data set. Okay. So, by the way, for those of you that are noticing, I'm using betas as similar to my decision variables, whereas the randomness is being looked upon as the Z and W. Okay. So here's what's going on. Statisticians, for those of you that have taken stat classes, you know they always call those random variables X's and Y's. Okay, of course, I'm not about to relinquish my X's and Y's to the statisticians. So I'm going to hold on to the X's and Y's as the optimizer and give the Z's and W's to the statisticians. Okay.
Statisticians like Z's for binary variables anyway.
Yeah, true. We do too. But the reason I picked up on Z's and W's, to be honest, is that the human genes are X and Y's. Bird genes are Z and W. And so I'm putting birds and humans together in this setup. So that's my reasoning here, actually, originally. But anyway, the point is that we're going to keep the decision variables as the X, Y's, and so on. And then the Z's and W's are going to be in this presentation, the statistical quantities. So anyway, this is the formulation, but if you look at it, this formulation is essentially like your sample average stochastic programming problem. These deltas are the H of omegas, the H function here. Given a beta, I can calculate the H. So this here connects it to stochastic programming. So again, if you're solving this problem, you're doing optimization for learning, right? And what I'd like to mention is that this kind of statistical learning can create basic regressions or other kinds of problems as well. So here we had a SVM, whereas more general statistical models might look something like this. You might have a linear regression, which is like this, where the model has some coefficients and then the variables are multiplied by these coefficients. So this could be a model, and then there is an error. Or you could have a nonlinear regression where this z is replaced by phi of z, and there could be other. I mean, you could have a neural network where these functions can be something like activation functions, which are sort of non-smooth functions. Okay, you could have slightly different versions of these functions, such as, so this zj here is along a given axis, right? Every phi has its own axis on which it's operating. It doesn't have to have that. You could have another kind of direction along which you have a function. So instead of having just the coordinate directions, you could have other directions as well and create a model from that. Those are called projection pursuit. So you can have a variety of these kinds of models that go into your statistical modeling. Okay, so right now, here and now, you should be able to tell that if I have a variety of statistical models and a variety of optimization models, the whole combination of things that you can do with that can be enormous. Right? A whole variety. But the question will still arise, which of these should you use? Okay. All right. Let me go a little further. So there could be, you could have a vector of errors as well. So in the first case where we had just this quantity, then this just means if I have a linear regression, I have the plane, and my errors are capturing deviation along the normal, and that's it. So I'm pretty certain then about what the coefficient of the normals look like. If I have nonlinear functions, then that could be again the same way. I have a curve and a deviation that moves the curve. Okay, but you could also have a situation where in linear regression you could have the plane itself be wobbly, right? That's another kind of model. Okay, so for all of these models, you could create a pairing with an optimization problem. And then which of those together could be the real situation for you? Okay, that's the kind of question I want to answer. All right, so let's take a quick look at what this means in terms of a modeling protocol. Okay, what would happen typically in a statistical learning situation is you get a data set, you divide up the data set into two segments at least. You have a training data and you have a validation data. And the purpose behind the training data is to use the training to create your parameters, all the betas that you might want to create, and then test that out by using the validation data. So the validation data becomes a proxy for the real world. Okay, so we should do at least this when we're doing stochastic programming. Should at least do this, not necessarily use all of the data points that I have to create my distribution, because once I create that empirical data set, if I use up all the data, I have nothing more to use for predicting what the decision maker might see in the future. At least if I have a validation data set, I could use that. Or better yet, if I use all the data, perhaps I should use a simulator. Perhaps I should use a simulator here to try to validate whatever decision I'm making. Okay. What we do with what I'm going to try to do is insert another box in there, which will be the optimization box. Which is, so what I will do is, instead of just having it this way, I'm going to install another box in here, and that box is going to be an optimization box, and that will be my LEO protocol. Okay, so let's see how I can set up the optimization problems, and then I'll draw a box like this. So let's go into putting this. So you can think of what these LEO models are really composition of parameter optimization and decision optimization. You got two classes of optimization problems that are residing together, and the hope is that by putting these two optimization models together as a composite stochastic optimization problem, we will be able to get a variety of systems modeled this way. The key here is going to be that we're going to live off of data, directly off of data. You're not going to need to hypothesize a scenario set, so to speak, because what I'm going to do is show you how to fit the statistical model to the data. Now take that statistical model and make it part of the optimization model. And those two together should be able to give me a data-driven decision model. Okay. So the question though becomes, when it is in the world of just parameter optimization, then we just use optimization to get the parameters. Here's what I'm going to do both, optimizing the parameters as well as the decisions. Okay. So in order to do that, I'm going to need some modeling tools that I'm going to introduce here. So the first thing that I want to look at are problems of this nature that are slightly different, because what happens in statistical learning, let's go back quickly to this class of problems here. Suppose I have a model M, okay? Let's say I have a model M, and this here is the prediction for a given Z, and for a given Z, how do you make a prediction here? When you do statistics, how do you make predictions? You have a model. What do? You forget about all the errors, right? The errors are 0. You just use beta times the functions. So if there's Z's, beta times the Z's. If it's phi of Z, beta times the phi of Z. The errors are all set aside because that's the prediction. Okay, you and I couldn't handle it if they said, well, my prediction is that that the interest rates are going to rise plus or minus something. They typically make a prediction which says 2%, growth 2%. Okay. Now, if I'm going to include this in an optimization model, I really don't need to have a deterministic quantity. I can take whatever model you're giving me, I can use that as part of my optimization. Okay, and that's what I'm going to try to show you how to do. Include the stat model into the optimizer, and let's see what happens. In some cases, it'll be very difficult, but my first hope here is that I will take the simplest problems first. Okay. The simplest problems will need certain assumptions, and I'll show you what assumptions will make it simpler, and then we'll go forward from there. Okay, so let's come back to this particular question. So this question over here is one where I have changed this expectation by doing the following. I've said, suppose that I have covariates, which is what the statistical learning world does. I have covariates which are W and Z, but once I observe the Z, I should be able to predict what the W will look like. You see what the distinction is between this and the previous model? The previous model was saying I took omega I. Omega I was W and Z together. Okay? Now I'm asking you, this is a conditional random variable. This W given Z, Z has been given. So for instance, in your inventory models, you've seen the past. Based on that history is this little Z. Okay, based on that history, you're now going to predict what the next set of demands are going to be. That's the W. Okay, if you gave me a different Z, different history, I'll get a different prediction. Okay, but the problem is to solve something like this. Okay, You can also have situations where you have these z's taking values in the same space as your decisions, the x's. That's sort of different from what you typically see in stochastic programming. These are called problems with endogenous uncertainty, which means that, so I'll give you an example. Let me quickly go to, let me skip this here. Let me show you an example data set. Just let's focus in on this part, this data set. This data set here shows me that I have placed some ads in the past on TV, placed some ads on radio. These are the number of slots of TV and radio ads I've placed. And what I've seen are my sales, my total sales being these quantities. Okay. So if those are, so if these are the random variables, then what I'm trying to do is to predict how much the sales will be given this data set. Okay. So let's see what might happen with this kind of a data set. So if you look at the data, this is the linear regression fit, and so you can see that the model is just a linear regression in this case. Okay. Now where does the X come in? Consider the CEO of the company. They want to decide how many ads to put on each TV and radio. Okay, so they come to the analyst and say, I really want to know how many ads to put on TV, how many ads to put on radio. The analyst turns around and says, well, those are random variables. You can't decide on random variables. So who's right here?
Well, CEO, just because he's CEO.
There you go. The CEO is right. Because CEO is the one who's putting together the funding for this project, right? So the fact is that for the analyst doesn't really know the process that converts the investment into sales. And that's why they're saying it's random, right? But the actual decision maker doesn't know that either, doesn't care. What the decision maker wants to know is, how should I put my money, where should I put my money? Okay? These are problems where you're betting. You're basically betting, right? Your bet is that I'm going to put some money and something is going to happen. I don't know exactly what's going to happen, but there will be some distribution that I can predict based on past data. Okay, and these are not real. These are not the distributions in the sense of, these are just observations, empirically observed data. Okay, so let's go back and see what the differences are. So I'm going to go back and do this model. This is a model that I actually created by looking at examples in 2 books. Anyone here used Hillier and Lieberman? I'm sure you have at some point or other.
Yes.
Yes.
We don't use it now. But
You don't use it now, at some point or other, right? So Hillier and Lieberman has this terrific example. They call it the WYNDOR example. It's the first example in their LP book. The WYNDOR example, it goes as follows. I have 2 classes of doors to make. Aluminum doors and I think more fancy doors, let's say. And the 2 sets of doors use 3 different types of resources. And the 3 different types of resources are, each resource is dedicated to one of the different doors, so that's 2 of them. And one resource is joint. So there's one plant, I think, that does the painting. And the painting one is the joint resource. Okay? So the goal is to maximize profit. And the profit maximization problem is stated in the following way. If I make door type A, I make so much profit. If I make door type B, I make another kind of profit. And then comes a linear program, maximize profit. Okay, 2 variables, 3 constraints. Beautiful example. But the first caveat, and these are very smart people, when they write books like this, they're very smart. What they have said is, the first caveat is, we assume that the sales are not a factor. However much you can make, you can sell. Okay? And the fact is that in many real problems, you can't sell any amount you make because there is a demand for your product. And so how do you predict that? And so I figured I'll take another book, a stat book, to look for data on sales. So that data set that I showed you was the data set from a stat book. Okay? So in the stat book, it gives you from the past investments on TV and radio, here's what the sales have been. So what I'm going to do is to take the Hillier and Lieberman problem and add another sales constraint. But the sales constraint cannot be a fixed number because you don't know how much you're going to sell. Right? Even if you knew how much TV ads, how much radio ads, you don't know what the exact sales will be. Right? So what I want you to remember is that this is completely data-driven. Although I'm going to show you numbers that are from a textbook, you can do all of this in any environment. Okay? And so the problem that I set up looks like this. I want to maximize my profit. This is the cost of ads. This is my expected value. And I'm going to now solve a problem like this, let's say. And look at this problem. This has a slight issue here. Let's take a look at what's going on here. What I've done is I've put the sales over here. YA and YB are the total amount produced, and this is the sales data. Are you with me? This WI is the sales. And up here I've put a penalty. Penalty between, because I don't know that I can use all of the ZIs. I can use only some of the ZIs that are close to the X that I'm at. Is that making sense? Suppose I were to do, for those of you that are statisticians, everybody know nearest neighbor type predictions, right? So if I'm given an X, I can take the nearest neighbors to the X and pick that as my prediction of what the W might come out of. Okay, so this penalty here is the difference between the data point and X, because it shouldn't, when this is 0, the M doesn't matter, and that's the accurate thing to do. When the difference between Z and X is 0, I can use the W. When the difference between Z and X is very large, I shouldn't be using the W, so I penalize it. This would be the stochastic programming model of the current situation. And this would not actually work. Okay, and let me show you why it wouldn't work. If I did this sample averaging, this is the sample average, right? If I did this, this would not work. Because what's going to happen is that if I choose my M's in a certain way, whatever M's I choose, my objectives are highly dominated by the M's. If the M's are small, my objective looks positive. If the M's get larger, my objective becomes negative. Because my penalty has become so large. Okay? So I can't do this stochastic programming, for instance. And the reason I can't do it is because even though the decisions may look reasonable, I don't know. After the fact, I'll show you that some of these decisions are reasonable. But take a look at what the differences are. This here is what the model sees. Okay? This is what the model sees. This is what comes out of the validation. Does that seem reasonable to you? I sort of led you astray here, right? Because what I've done is I've created a stochastic program to do what I tried to do, and the stochastic program is not giving me appropriate responses, because you see, this objective that the stochastic program is seeing is not even close to what it's being validated. And why is that happening? It's happening because I am using a completely data-driven setup. Okay, so my first lesson here is that there's a lot of hoopla about data-driven decision making. We have to be a little careful about this hoopla with data-driven decision making, because if you did not do multiple models, all you did is this, you will not be able to predict. So this quantity is nowhere close to this quantity. Actually, the best numbers come out over here. From these numbers, maximum profit is approximately here, right? 38.91 to 40. That's the maximum profit. Okay? But the stochastic programming problem predicted you would have a negative 269. And why did you have a negative 269? Because those penalties are arbitrary. Those penalties that came into the stochastic programming problem were arbitrary, and you cannot validate it. That's the issue. So a lot of times you will read in a paper that I have a random constraint, and whenever there is a deviation, I'm going to penalize it. That penalty, if it's not coming from real costs, such as holding cost or something like that, it is going to give you something like this, and you're chasing down a rabbit hole here. Okay, so what should we do? Okay, not completely data-driven. Data-driven itself is not bad. I want it to be data-driven, but there has to be some modeling that goes into the data in order to be able to get something that you can validate. And let me show you how to do that. Okay, so now what I'm going to do is, so the first thing is we cannot use this SAA thing directly, because even if you had the penalties, you can't use the SAA thing directly in this situation. Okay, so what we will try to do is, let me show you about 10 minutes? Okay, I think I can do this. Okay, so what I'm going to do now is the following. I'm going to replace these distributions here. So this needs a distribution. I'm going to replace this by making some assumptions. And the assumptions are going to be the following. The first thing I'm going to do, let me skip through all of this, I'll come back to it later. What I'm going to do is this. I'm going to make some assumptions to avoid the curse of dimensionality, which is the following. First thing I'm going to do is to make the assumption that if I do a statistical model, my statistical models will be such that my errors are not going to be dependent on the specific decision that I'm making. So the errors themselves are going to be what we call homoscedastic. Okay, which means the error is the same, but the variation is not. Okay. What else? I'm going to assume that that I can allow a variety of different kinds of models. Okay, so there could be models of this nature, there could be models of that nature, and from all of this, I'm going to try to select which one is going to give me the best predictions. Okay, that's the next thing. A second thing about curse of dimensionality is this question here. Okay, so we've got two models, a statistical model and an optimization model, right? And both models are optimization models in some sense, right? If you've got a large data set, then you've got two huge optimization problems that are intertwined, okay? I am not really going to get deterministic optimality for this problem. What I'm going to try to do is to choose a decision which is very good and is most likely to be very good. How do I quantify that? I want to have a good decision which is likely to be very good. That's what this criterion is saying. I want a decision X which is close to being good. That is, this delta x belongs to the delta argmin of this function. So my x is not exactly the argmin, but it's some approximation of the argmin. And the likelihood, the probability that it is very good is greater than a certain number. This is a slightly different way of stating optimality. It's a relaxation of deterministic optimality. Because deterministic optimality would say, give me 0 here, so argmin of f of x, x in x, right? That's the deterministic optimization problem. What I'm saying is I'm going to ease up on that requirement, and I'm also going to ease up on this requirement, but I'm going to ask for the probability that it's high enough, that it's good enough. Okay? What this does is the following. It puts us on a path to do two things. One is inexact optimization here, and this comes, the probability comes from replications. So if you sample, and you run in parallel, what you're doing is replicating these optimization problems. And what you want to be able to do is to ultimately get a sense of how likely is it that you have a reasonable decision. Is that making sense? At least intuitively? Okay? And we can actually compute with this. Because what you can do is take each thread of optimization, run its own sample average approximation, and I'll show you how we do that. Run its own sample average approximation, and at the end of that, I will be able to estimate what this probability is, because what am I doing after all? Remember, every probability book, the first thing it does is, how do we define probability? We go into experimentation. Right? This is my experiment. And with this experiment, I can determine how far, for each case, I can determine how far I am away from optimality as long as my problems are convex. So this is my first step. So in my first step, if I have a convex optimization problem, I can predict how far I am from optimality. And then I can say that overall, putting all these together, how far am I from optimality on the overall problem? Okay. So that's the next thing. There's a third thing I'm going to do, and that is the following. I'm going to run by this one really quick, and that is when you run optimization models in parallel, you're going to get different answers. All of the answers will be different because they are all sampled, right? What should we do? My suggestion is what in statistics they call bagging. We did this earlier than we knew this bagging idea, but the bagging idea is the following. You take each of these functions that you just say you did benders. Each one gave you an approximate objective function, right? When you solved each of those independent samples, you got an approximate objective function from benders. Take those objective functions, average them. That's the aggregation part of bagging. Average those functions, optimize that averaged function, and this decision you get from that, you compare to the average decision. Average objective, optimum, compared to the average decision. If those two are close, then you're done. That's this new notion. And so with these three assumptions, we can solve some problems. And let me go and show you some numbers. I'm going to skip all this math stuff. It doesn't matter. I'm going to come here and show you some computations. So this is the statistical learning part. That statistical learning goes into the learning-enabled optimization side, and then you do some validation. I want you to notice one thing. Although I'm going to talk about it as though I went from here to here to here, it can happen that I go here and I go cycling back. I can do this cycle back and forth between the statistical model and the optimization. And then come down to the validation side and ask if the decisions are generalizable enough. And the term generalizable is borrowed from statistics again, where generalizability is how the model will do when it is implemented. Okay, so let's. I'm going to skip through all of this. I'm going to show you the numbers that we get out of that problem. So here is, first off, this one is that since in linear regression, if you have, we were using linear regression from that textbook, it turns out that these 8 data points here, there are 4 here, 4, no, yeah, that's 4 there, 2 there, 2 there, 9 data points. There are 9 data points that are outliers out of a data set of 200. So you remove the 9 data points, and what you get is a much cleaner fit of the linear regression here. When you get that linear regression, then you basically take this part as being the linear regression, this part as being the optimization, which is now going to be the following problem. We did the problem earlier. We didn't show you what the problem is. This problem here. So what's happening now is that it's the same as before, except that now I have a statistical model here. Notice there is no penalty. There is no penalty in this formulation. And there is no penalty because I can predict what the errors and M are going to be using statistical modeling. So once the betas are known, I stick that in here together with the error terms. And these error terms can be, when you run a regression, what do you get out of the regression? It tells you that the bias term or the beta 0 has a normal distribution with a certain variance, right? A 0 mean and a certain variance. If you run it with you could have covariances between the error terms as well, right? So it comes out with a variance covariance matrix. And the variance covariance matrix gives you what the normal is on the multidimensional version. So you get this coming out of the linear regression model or any other kind of regression model you can get, the distributions of the parameters. Take those distribution of those error parameters and stick them in here. So this M has actually got not just the linear regression, but it's got the error terms in there so that depending on which model you choose, you could have the error terms making the sales prediction go parallel to the plane, or the plane itself starts excuse me, wobbling. Okay, and that's the model that goes in here. That's the model that goes in here. So there are multiple types of models that you can stick in. And so here's what will happen. What we will get are multiple outputs. So this output here is if I just did the LP. If I just did an LP, and how would I do the LP? I would take the linear regression and just forget about the error terms. Stick the hyperplane in there. And here's what it does. It gives you a solution. It predicts that you'll make so much money, 41,391. The validated objective is 38,000 to 40,000. So this is what you expect when you stick in the deterministic objective. The optimization problem is going to overestimate in the maximization problem. It will overestimate what you will make, and that's what this is showing, that the LP is estimating you'll make 41,000. The validation says you'll make less. Okay. And actually, since this is a 95% confidence interval, what the hypothesis test will do is tell you that this objective is not seeing what the validation set is seeing. Okay. The other model is this one here, which is the normally distributed but uncorrelated coefficients. So you have the beta 0, beta 1, beta 2. Those are all coming out of the linear regression together with the variance covariance matrix. But what I'm saying is, how about I ignore the off-diagonal terms of the variance covariance matrix? What I will get is another model. And that model turns out to give you a different X, a different predicted objective than the LP, but this predicted objective falls inside the 95% confidence interval. Okay. It says 41,580. This says between 41,000 and 42,000. So I cannot reject the hypothesis that this model could be okay. Okay. And notice I can actually calculate these quantities. The probability that I'm close to 0.7% of optimality is 96%. I can calculate that probability because I've done this other processing on the side, the parallelized solves, replicated solves. So this is a notion that we borrowed from simulation optimization, replicate. But the replications here are being done with a little more tuning to optimization than in simulation optimization in general. All right, so let me show you some more. So I could do correlated. So if I took the whole variance covariance matrix instead of just taking the diagonal terms, if I took the whole variance covariance matrix, then my prediction is 41,492. I'm here again 41,469 to 42,261. So I'm still within that, and therefore it seems like a reasonable model. Okay. Now, so far, I've not done any comparisons across models, actually. All I'm doing is looking at how each column fares. Okay. Ultimately, I will do across models as well. So let me go ahead and put up the other models. There are 3 other ways to look at it, 2 other ways to look at it, and you get some predictions. So this one has a different X. See, the X's look quite different overall. But the prediction values, the main thing that you want to notice is that these predictions are all within this interval, except for the LP one. The LP one doesn't fall inside because you solved the deterministic problem. Clearly, you didn't see enough, and so you can't expect to see exactly what the uncertainty will say. Okay, so I'm going to compare that with what happened earlier. What happened earlier, I got this as the best, but not even close. These values weren't even close. Okay, so in other words, just blindly putting the data-driven idea out there is not such a great thing to do. If you use the model, you can still go completely by data. We're not hypothesizing any distribution, really. We're just using what comes out of regression models themselves. Those are also approximations, but let's see whether those approximations can be used for validation, and you can. So I'm going to skip through all of this. This is actually the test of each of these models. And then finally, we decide whether, so this was the one that gets rejected. These other ones don't get rejected, but now we want to compare which one of these decisions we should take. And the way we do that is by creating these stochastic dominance charts. The stochastic dominance charts tells you that the objective function that you're seeing for the LP looks like this, and the average is what is being reported, but the actual validated curve looks like this. And this is worse in a maximization sense than either of these two. Because the chances of you hitting here is much higher than chances of you hitting any of these. Does that make any sense? But this can actually be quantified. We don't have to do just pictures. We can actually quantify them by doing what they call a non-parametric ANOVA test. So here you can see that the small p-values tells you that one model beats the other. So in this case, these models, all these models beats this one. In this case, these two models beat this one, and again, this one, small p-values beat, so these two beat that one. And finally, these two models are pretty close because this p-value is not that small. This p-value is really, these other, the ones that are 10 to the minus 7, that means that they have very small likelihood of being beaten by the other models. Okay, so with small likelihood, you can toss those, but these are not so small. So these two are about equivalent models. So these two are equivalent models, these other ones. Anyway, the point is that in all of this, my suggestion is that we be careful about just saying data-driven, data-driven, data-driven. I have to take some responsibility myself for this, actually, because I don't know if some of you know, my email address is sen@datadrivendecisions. sen@datadrivendecisions.org. So I do take some responsibility for the hoopla. You can't just, I mean, we're all doing data-driven, but the thing is, it's different in the sense of using a model to infer. The statistical model is inferring for us some distributions. And from that, we just use those distributions that were being inferred from the stat model. And then we're comparing a bunch, not one set of scenarios. That doesn't, in my opinion, do the trick. Anyway, I've taken way more of your time than I originally intended. It's gone way over.
Questions?
How large of problems have you solved with this kind of approach?
It depends on what you mean by this kind of approach, because there's a bunch of approaches that are stuck in here. Okay, so we have solved with, so there are two classes of problems that I mentioned. One is capital Z equals little z, and one is capital Z equals little x. When capital Z equals little z, which means that the uncertainty is endogenous, okay, then we have solved problems that are for electricity, the state of Illinois, the entire state of Illinois, their electricity planning problem we can solve. Okay. When little z equals little x, like in this example, where the uncertainty is endogenous, then we're solving small problems so far. We're not solving large problems because that cycle is a lot more complicated. So for some, we can solve large ones. For some, we can't yet. So the state of Illinois problem as an LP to be solved within, they give you 5 minutes to solve the problem. And that LP has several million rows and several million columns if you solve it as an LP. When you do it in this way, you decompose the problem. It's much faster, and we can do it in the 5 minutes. The LP with 5 scenarios takes 20 minutes on CPlex, 20 minutes on CPlex, and we can do it in 5.